Hey guys, welcome to the third video in our discrete energy and radioactivity unit. This time we're going to be looking at the energy diagrams, or if you are following along in the chapters in cognitive, that's 7.1.2. So what we're seeing in front of us is the energy level diagram of hydrogen. So different gases will have different energy diagrams, and that just means that the excited states and the ground states would have different energy levels. Okay, and they may have also different numbers of excited states. So hydrogen here we can see has 5 potential excited states before ionization. So a quick little review of ionization is an ionized gas is a gas that is charged. So what we're normally looking at here is that our hydrogen atom has one proton, so it has a plus charge in the nucleus, and it has an electron orbiting it. So ionization is that it gets, in terms of what we're talking about in physics, is the gas itself, in this case hydrogen, gets so excited that this electron says bye-bye. So the electron gets thrown away due to its overexcitement, or it's taking on too much energy. So when too much energy is given to the electron, it becomes ionized. So what that means is it gets thrown away, and then hydrogen itself normally would have been a +1 and a -1 charge, which the net charge would be 0. Because it's throwing away the electron, it now has a net charge of +1 when it is ionized. Okay, so that's a quick little review of ionization is what we're talking about here. But we usually don't talk about it being ionized. We talk about the electron switching between these different states. And I think there's some really, really good diagrams. This is a really, really good diagram here, where it actually shows the electron can switch between any number of states. So I'll walk through this a little bit slower with you guys. So what we're really saying here is that an electron, supposedly it was already at, let's say it was at state 3. Whoops. So it was at state number 3, or n equals to 3. So it's a second excited state. And what can happen? So it can give off a photon. It can give off a photon, and it can change states. It can also go directly to the ground state by giving off another photon with even more energy. And so it's got 2 ways that it can change states. It can go directly to the ground, or it can go to the second one. Now, if we go back one more even, you'll probably start to see the pattern. So if we start at this one, n equals to 4, n equals to 4. If we start here, if that's our starting point, it can give off a photon to reach n equals to 3 state, the second excited state. It can also, from that point, also give off another photon to reach that state. Oh, actually, I think I missed another one in the previous talk. So it could also give another photon from that to reach the 4th one. So it could give off 3 different photons to transition all the way to the ground state. It can also jump directly to the first state. That's another photon. And finally, it can also jump directly to the ground state there as well. So that's adding another one. So what that really means is that there are potentially 5 different photons that can be given off to make that transition from the fourth n equals to fourth starting state all the way to n equals to 1, the ground state. And this is just a diagram just to show that it can jump from, so this is going from states 4 to 3. This is going from state 4 to state 2. This means it's going from state 3 to state 2, state 3 to 1, like that, state 2 to state 1, so this line right here. And this is probably the mega line from state 4 all the way to state 1. Okay. So this could be one of the questions that you get asked, is that it might say a hydrogen atom, like it is now, is in a certain state. How many distinct photons that have different wavelengths or frequencies can it emit? Okay. So here the answer is 1, 2, 3, 4, 5, 6 different ones as it goes from N4 to N1. And I think that's somewhat similar to what we've got here. Am I missing one here? There's 5. There's supposed to be 6. Let's see here. I've got the one going straight down. Oh, I'm missing this one, aren't I? Hold on. I'm missing this one. Yes, okay. So I'm missing this jump, aren't I? From state 3 to state 1. So there's our last one, our 6. Okay? So 6 different photons that can be emitted. Okay, that looks a little bit better now. Okay, 6 different photons. Good. So lastly, we can obviously also get the look at the energy levels, and from the energy levels, you can actually work that back to figure out the frequency of the light or the wavelength of the light. So you can kind of see that they've actually got this already, they've color coded it for you here. So they're actually telling you, we can actually try to sample a little bit with that ourselves, is you can take the energy levels. So again, we're working backwards from our formula here. E equals to hc lambda. And so if we want to figure out what color of light it is, we'll just rearrange this equation first. Hc over E. We do our substitutions for Planck's constant and the speed of light. And I'm getting a little bit lazy here, so 6.63 times 10 to the power of negative 34. 6.63 times 10 to the power of negative 34, that's Planck's constant. Speed of light, 3 times 10 to the power of positive 8. And then our energy, which we'll actually have to convert that back into joules. So we're going to take 1.89 and we're going to multiply that. This is in electron volts. We're going to multiply 1.6 times 10 to the power of negative 19. That has to go inside of there, and then we will get our wavelength, which according to this should be a red color here. So right, let me make a quick little calculation there to see what we might get. Okay, so we got 6.63 times 3 divided by 1.89 divided by 1.6. And so it looks like we have about, I think we can end up with about 650 nanometers. So 650 is pretty close to the red color spectrum. So that's giving us about 650 nanometers, which is a pretty close approximation of red light, which is why they have the color red there. Okay, that is, I think, about it. There aren't too many questions associated with this first part, so really take your time to understand the basics, work with the formula, get used to changing between joules to electron volts, or from electron volts back into joules, as I've just done right now. And think also a little bit about the energy level diagrams that we've just discussed. And we'll see you guys in 2 days.